Welcome and thank you for joining us for today's webinar, How AI-Enabled Smart Cameras Can Revolutionize Seafood Inspection, brought to you by Seafood Source and sponsored by ThisFish. We have a few housekeeping notes to go over before we get started. If you need any technical assistance, we first recommend refreshing your browser. If you continue to have technical questions or issues using the On24 platform, please use the Q&A box and I will respond as soon as I can. There will be no call-in number for today's session. To connect, you need to have access to either a computer, tablet, or cell phone audio. Everyone has been muted. If you happen to get disconnected, you can log on again using the instructions provided in your webinar confirmation email. If you continue to have trouble, please email info@seafoodsource.com and we'll respond as soon as we can. For your convenience, everything in the webinar console is fully customizable, so you can move things around, resize the window, and even turn on captions for this event. At the bottom of your console, you'll also find a resources box where you can download the slides as well as any additional content for today's presentation. And again, speaking of questions, you can ask questions at any time during the presentation by submitting them through the Q&A box. We'll do our best to leave some time at the end of the session to answer as many questions as time allows. And finally, this webinar will be recorded and you'll receive a thank you email with the on-demand materials within 2 business days. And with that out of the way, I would like to introduce our speakers for today. We'll be hearing from Eric Enotam, CEO and co-founder of ThisFish. Eric is a technology leader in the seafood industry and has spent the past 15 years developing innovative solutions for seafood supply chains and processing plants. He was born and raised in a commercial fishing family in Canada's North Pacific. We'll also hear from Melina Thomas, senior data scientist at ThisFish. Melina builds AI solutions for seafood processing, combining machine learning, computer vision, and generative AI with real-world impact. Off the clock, she's a poetry-scribbling, trail hiking, food-loving traveler who enjoys blending technology with creativity. At this time, I'd like to welcome our speakers and hand the webinar off to Eric.
Thank you very much for the introduction. And yeah, I'm excited to get the webinar underway today. So how AI-enabled smart cameras can revolutionize seafood inspection. Before I get into the presentation, I'm just going to give you a little introduction about our company. So ThisFish, we're a Vancouver-based software company with staff in Latin America and Asia. And our mission is really to help drive profitability and sustainability in the industry through better data, basically make that data digital, real-time, and actionable. And we do this by providing software and AI to seafood industry to help them automate and digitize all their data in real time with tablet computers, IoT devices, and smart cameras on the factory floor. If you want to learn a bit more about our company, you can go to our website at this.fish. And a little bit about myself. I'm actually born and raised in a commercial fishing family here in Canada's North Pacific. My father, grandfather, and great-grandfather were all fishermen, and I grew up in the industry. Well, one of the reasons I mention that is because I think it's very important for the industries to start to learn about some of these new AI technologies, because it's not just the data scientists and the AI engineers that are going to lead to the successful adoption of this technology, but it's really going to be industry players, people with a lot of domain knowledge, and people who understand what the challenges are in the seafood industry. So I'm really excited about today's webinar. And we've sort of divided it into three components. First is the basics, so AI 101 and how basically computer vision works. I'm going to be asking Melina to step in and give part of the presentation there to explain how AI works. Next, I'm going to look at use cases. The technology is extremely versatile, and I'm very excited about what the potential use cases are in the industry. And then finally, a few short words about what the future holds for AI, what some of the opportunities and challenges are in the future. So let's get to learning goal number one. So AI, as we know, it's really everywhere, and especially computer vision technology. It's now in our phones with facial recognition, with barcode scanners, CCTV, even in our cars. And it's really part of what's considered the fourth industrial revolution. The first, of course, was the steam engine in the late 1700s, followed by electrification and mass production, and then computers and automation and electronics in the 1970s. And today we're in Industry 4.0, which is really about digital data, AI, and Internet of Things, and that is sensors, basically. And AI falls into a broad category of what's called data science. And it's really about AI represents the simulating human intelligence in machines. A subcategory of AI is called machine learning. And it's really about machines making decisions without being programmed. So we hear a lot about training AI with data. So basically, we can teach AI with data. A third type of AI, which is kind of a subset of machine learning, is called deep learning. And it's really about using artificial neural networks to solve extremely complex problems or to see patterns in very large data sets. And now we all know that another subset of deep learning is generative AI. And most of us have been playing around with ChatGPT, which can generate content or analysis. There are also image generation AIs out there like DALL-E. And this uses large language models, which are also based on neural networks. So that gives you a bit of an overview of the technologies that are currently in use today. And computer vision technology does use neural networks. And what is AI really good at? It's really good at seeing patterns in large data sets. So here we have two problems, and the one on the right or the one on the left, the A problem, has only two variables, and we can basically, understand what the output is. But the problem on the right is much more complex. There are four variables. And AI is really good at teasing out what the algorithm or the solution is to these complex problems. And so here you can see what the AI has determined versus like what we could mathematically. So computer vision works very similar to human vision in the sense that human vision has some sort of sensor, an eyeball, and our brain is a processor. And computer vision works in the same way. There's typically a camera and then a computer, with a processor, where we take an image and then we process it and analyze it to understand it. But unlike computers, we see the world very visually. We see visual patterns in data, whereas what the computer actually sees is numeric patterns. So basically, every pixel in an image is converted to a number, and then the AI can understand and recognize patterns in the images. So it could understand the difference between a cat and a dog based on the numeric pattern in the image. And computer vision has been around for quite some time. And in fact, there's been an ImageNet large-scale visual recognition challenge that's been going on for many, many years. And you can see in 2015, AI actually started to do a better job than humans in terms of recognizing images, and their error rate was below 5%. And computer vision is used a lot in the seafood industry, particularly in aquaculture. There are a lot of underwater cameras that are being used to look at fish health, fish growth, and feeding patterns. In the commercial fishing industry, there's a lot of cameras on board vessels doing electronic monitoring of harvest and then using computer vision algorithms to determine species that are being caught or counting fish and this sort of thing. But there's actually not as many providers of computer vision technology in the production quality control space. You can see here in this graph, there's a lot of technology providers in the aquaculture industry, some in fisheries, and a lot fewer in quality control and production. So I think that there is a lot of opportunity for expansion and the use of this technology, both in the fish processing, but also in the supply chains as well. And so with that, I'm going to now just turn it over to Nalina, who will walk us through really to give us an understanding of how AI really works, how we can train it, test it, and refine it. So Nalina, I'll just pass the slides over to you now.
Yeah, thanks, Eric. So let me just give you a basic overview of how we train AI in seafood quality inspection, or be it any sort of similar computer vision projects. So it's basically about teaching the AI to see. And on a high level, it includes these 7 steps. The first being collecting images, videos, or whatever we are trying to teach the machine learning model. We prepare the data in such a way that the model can ingest it, it can understand it, and then we choose a machine learning algorithm which can solve the kind of use case or the problem that we're trying to approach. We train the model, we test the model, we make a few model adjustments if necessary, we retrain it, we fine-tune it, and then we deploy it. Now, let me walk you through these 7 steps and explain what each of these means. So the first step is basically collecting images. It's like teaching a child by showing pictures. And this one, let me just play the video. Yes, I think it should start on your screen. So this is basically a camera placed on top of a conveyor belt, and it's capturing images of salmon fillets running on the conveyor belt. Now, this data can be used to train a model that can detect salmon fillets. If we want the same model to be capable of detecting defects on the fillets, we just need to make sure that defective fillets are also part of the data set. Another example is cans in tuna canneries. So we collect images of tuna cans in order to build a model that can identify, recognize tuna cans. Again, if there are defects in the tuna cans that can be seen from the top, like how we see, like how a camera would see from the top, then we need to make sure that such defective cans are also part of the data set. This is an example of how we're collecting images in a tuna cannery. We can adjust if the frame rate of the camera, like should we be collecting 5 images per second? Should we be collecting 30 images per second? All of that can be adjusted based on what the camera configuration supports and what we actually need. So, and it's not necessary that we always collect images from the product line. Say there is a can that has a part of it underfilled, or there's like an incomplete portion of it. And this is not a common occurrence on the product line, but we do want the model to be aware of such cases, to recognize and, to point out that this is not just a can like any other can, it's also an incomplete can, maybe trigger some actions down the line. So for such corner cases, maybe cans with incomplete portions, or maybe some blood spots, bruises, bones, skin, scales. So all these corner cases, we can collect data even in a controlled light setup box, like how we've shown here. So we actually did this in a tuna cannery recently. Basically, the AI needs to know the good and the bad examples in order to learn, just like how any human being would learn on the job. And now that we have the data collected, we need to prepare it. So we need to label and teach the system, hey, look, this is a fish, this is a can, or this is a defect, or let's say the shade of orange for this particular salmon fillet is 23. So this is what it is. So we need to teach the model, we need to teach the algorithm, this is this. So this is an example of how we do it. We use a software called Label Box. And we actually, I'm just playing the video right now so that you can see how we actually do it. So there's a tuna can, and we're drawing a tight bounding box around it. and we call anything inside it the can. You can also see a small incomplete portion there. We draw, again, a box around it, and we call it an underfill, or maybe an incomplete. This is the case with salmon fillets. We again draw bounding boxes across the fillets. We call it farm salmon. If you notice, there's a small grayish spot on the belly region. It's a defect. It's called inoculation. We again draw a box around it. We call it inoculation. And this is basically how we prepare the data set, especially for an object detection model. So we annotate it, and this is a clear case of a supervised learning. We are actually supervising what the model should be learning, which classes, how it should be identifying, what defects, how the boxes should be, and all of that. And now that we have collected the data, we have prepared it, the next part would be to think about what problem are we trying to solve? What's the use case here? And depending on that, we try to pick what kind of machine learning model we should be using. Are we looking at an image classification type of a problem? Let's say a whole salmon is passing on the conveyor belt under the camera. Maybe we want the model to say whether it's a male or a female. Now that's an image classification problem. Do we want something like an object detection, where it not just shows the object, but also like draws a box around it and says, look, this is a can, this is a defect. Facial recognition models kind of runs on most of our phones. We unlock our phones with our faces. Anomaly detection is basically about identifying any sort of outliers, any sort of defects, anomalies in the data set. Weight estimation, say a whole salmon is under the camera, and the model in the camera is able to predict the weight of the fish in kilos or pounds. And there is a depth estimation part as well there, which contributes to the prediction of weight there. OCR, being able to read through the barcodes to the text. Maybe an example would be a model being able to automatically tell if the product is expired or not, just by reading through the dates. Edge detection, there are models available off the shelf, ready on the internet, which we can use, which gives us the outlines or like the contours of the object in focus. And then there's segmentation, which basically kind of returns telling us which pixel belongs to what object. Like this is just an example of when I run a segmentation model on the top part of the fish, like over here, like this fish over here, it just returns me a green segmented area. It just says every green pixel in this picture belongs to this particular fish. Now, there's a lot of use cases that can come across this based on this as well, which Eric will walk you through later. So now we've collected images, we've prepared them. We also know what kind of model we should be picking based on the use case that we have. And we now move into training the model. So when it comes to training, we generally do like a 70-30 split. So we dedicate 70% of the data set only for training the model, and 30% where the model does not see any of it while training. It's just used for testing, to run the model predictions on and things. It doesn't have to be like a hard set rule of 70-30. It can be like 75-25, 80-20, based on a preference, based on the number of images that we have. So basically, the model is going to go through each of these images. It's going to learn through the patterns, find features that it can help distinguish between each of the classes that it has to predict, and it gets trained. And once it trains, we can test the model, and we go to the part where we'll have to evaluate the performance of the model. Now, especially in a computer vision scenario, before I explain the metrics involved, I think I should explain what kind of predictions are possible. And in order to explain that, I've just taken the example here where there's a defect detection model. So you can see tuna cans, and you can see that these two cans over here, which I just pointed out in orange, you can see that there is like 2 black spots there. So that's basically defects. So the first case here, there is a defect in reality, and the model is calling it out. So that's a true positive. The second case here, there's no defect, but the model is saying there is a defect. That's clearly a false positive. Now let's look at the third case. Now this is a bit concerning because there is a defect in reality, but the model is missing it for some reason. It's not showing up and it's going undetected. That's a false negative. And the last case being true negative, where it's a good can and the model is saying it's a good can. So the first metric being accuracy, it's basically how often the model is right on an overall basis. So we have 4 predictions here, of which 2 of them are right. So you can see that the true positive and the true negative are right. So it's like a 2 on 4 scenario here. It's a 50% accurate system. The next metric being precision. So precision is basically where we look at the predictions and then we want to understand how many of the predictions were actually right. So if you look here for the positive classes, for the defect predictions, so there are 2 defective cans that's being predicted as defective cans, but in reality only one of them was a defective can. So now that's again a 1 on 2 case. It's a 50% precise model. The third metric is recall, and it's one of the important metrics for us. And this is basically an indicator of, in reality, how many defects existed, among which how many did the model actually catch or pick up. So in reality, you can see that there are 2 defects over here, of which the model is only picking one of them, the first one. So that's again a 1 out of 2 scenario, and it's a 50% recall here. Now let's say we work in a bank, and in that case, maybe building a fraudulent transaction model would be important. A fraudulent transaction occurs, and if the model is classifying it as a normal transaction, that's probably a costly business because it can have repercussions. Similarly, from a food safety perspective, let's say there's a bit of metal in the tuna can, and the model is not detecting it. Now that can be a health hazard. So we've often heard of recalls in supermarkets where they take things off the shelf, maybe because it's defective or something to do with something if there is a health hazard or things like that. So in the similar sense, even here recall is basically a metric of how many positives were actually picked up by the model. How many did it actually miss out? And in object detection cases like this, we do want to have minimal false negatives. We don't want defects to go undetected. So we would try to build models with high recall. Yeah, so now we know how to evaluate models, and we have a test set that we already discussed. So we can actually visually go through the predictions there, and we'll realize that, okay, the model is also something like us. It has its own biases. It also makes errors. So we got to dig in and understand why is it biased in a particular direction. So for example, if you look here, these ones are the wild salmon on the right, and on the left is farm salmon. So you can see that these cuts near the tail region, so these ones, they're called gapes. So the model basically predicts them as gapes, which is right. And this cut on the belly region, on the top part of the fillet, is a trench. It does a similar prediction on a farm salmon, where the cuts on the belly region were also called trench. So we realized that these are actually not trenches. They're cuts on that muscle fiber over here, and it's actually supposed to be gapes. So we did go through and dig in and understand why the model might be predicting this way. We went through the data set. We corrected any of the biases that existed there. We added explicitly more examples of gapes in this particular region. We retrained the model, and yeah, the model was good now, and it was predicting gapes like how it should, regardless of whether it's in the tail or whether it's in the belly region. So in summary, this is just an overview of the kind of steps that we do in order to train a model. And I'm passing it back to Eric now. Back to you, Eric.
Great. Thanks, Nalina. Yeah, and I think the general rule for training computer vision AI is that if you can see it with the naked eye, then we can likely train an AI as well. And in some cases, the AI will maybe even do a better job because it can inspect things a lot quicker and faster. So if fish fillets or cans are going by at a very high rate, the AI can inspect it a lot quicker than humans can. So now what I'm going to do, I'm just going to quickly go through a whole bunch of use cases. And I think that this is one thing that's the most exciting for me, is that I see a lot of potential for the use of computer vision throughout the supply chain and seafood processing. So there is obviously a lot of visual inspection that goes on in the seafood industry on raw material, semi-finished or in-process material, and then of course, finished goods. And depending on, as Nalina said, depending on the type of problem that you're trying to identify, there are many different types of models that could be used to solve a computer vision problem. And I'll just go through some of them, give you some examples so you can get a general understanding of how flexible and versatile the technology is. So for instance, generally speaking, with looking at defects in seafood products, we're using an object detection model. That is, the defect is an object inside a photograph, and we're trying to pick out those defects. So here you can see some defects on a fish fillet. The defects could also be potentially on shrimp, whether it's black spots or broken tails or just a piece to classify the shrimp. Nalina talked a lot about canned tuna, lots of different types of problems with defects in canned tuna. And then also on the exterior of packaging. And so this is also very important from a food safety perspective. You can see there's maybe a defective seal, which could lead to a food safety issue on a can of seafood. And also on pouches as well. There's a lot of visual inspection that happens on cans and pouches to ensure that they're properly sealed for food safety purposes. We even had another customer who asked us about detecting the sex of a male or female lobster. And as you can see here, it's very visually clear the type of sex that the lobster is based on the underside of the tail. So generally speaking, how many images do you need to train a model? The fewer classes you have, so in this case, we just have 2 classes, male and female, and the easier it is to visually see something, generally you need fewer images to train a model. So in some cases, you might need thousands of images, and in other cases, you might only need a couple hundred images just because the visual problem is not that complicated, such as looking at a male and a female lobster. Color classification is another one. Obviously, this is very important in the farm salmon industry, where color is quite important. And in this case, we used a classification model where we'd segment parts of the fish fillet into different color categories and then analyze them. Nalina also talked about weight estimation. So, we've worked on some algorithms looking at estimating the weight of a shrimp or a squid, or in this case, a salmon. And for instance, on the salmon here, we got about a 98% accuracy, which is quite high. So if you're looking at helping to do grading, you could actually use a camera instead of a scale to do weight checking for size grading, for instance. And then this is a very interesting one. In the tuna canning sector, there's flake versus chunks that are put into the can. And the percentage that is flake is actually quite important. And you can kind of visually see it. So you can see the little orange here. And what we did is actually we used a segmentation model. So we basically fed the images into a model that segmented out the flakes because it was visually different than the chunks. And then because we knew the actual percentage of flakes in those cans, we were able to build a model to determine flake versus chunk in the canned tuna sector. We've also worked on other models that have maybe have not so successful. This one is looking at the salinity in frozen tuna. So you can see there's actually a salt ring on the outside of it. And so in this case, we used an edge detection model to try to analyze it and determine the level of salinity in the tuna. And then, of course, there's the optical character recognition models that are used to basically read characters. So you could use this to read the best before date or the production code on a can, or inspect a label and that sort of kind of finished good labeling. Now, while I think that there's a huge potential for quality control inspection just because it is so visual, there's also some use cases where you can use computer vision technology for production and for estimating productivity. So we can generate basically a computer vision model to detect when a can or a fish fillet passes by the camera. So we can in fact count and even estimate the weight of production using the camera as well. So in this case, what we've done is we're counting the number of cans that are going below the camera, and then also classifying when there are downtimes. So if no can comes under the camera will then register that period of time as a downtime. And so this allows us to basically develop an overall equipment effectiveness solution for the seafood sector, whether it's a packing machine in a cannery or a fillet machine, or maybe a blast freezer, any kind of machine. You could put a camera on the output of that machine and then basically track how many items are being produced and what the downtimes are. And then you can see here in this graph, all the orange bar chart is basically the downtimes, when maybe there is a break, or maybe there is a problem with the machine and no production was operational. So some of our other customers have also talked to us about the challenge of tracking employees in a production facility to understand productivity in different departments. Because sometimes departments are quite fluid, so people are walking between different departments and it's hard to gauge how much time was actually spent throughout the day. So you could actually set up a camera where you're basically tracking the numbers of workers and the time they're in a specific production area. If you're actually counting the amount of units being produced, that would allow you to then calculate sort of overall productivity for that area. We've also had some queries from some of our customers about looking at the quality of the task that a worker is doing. So for instance, a worker needs to put 10 or 12 portions into a box. You could have a camera inspecting whether the worker is putting the proper number into a box. Or for instance, a worker is loading a freezing machine, and the way that they're loading it could be correct or incorrect, which could cause the machine to jam. So again, you could also use computer vision to basically track whether the worker is performing their tasks correctly, which could help prevent costly mistakes. And another thing that you could potentially use is also inventory tracking. So in this case, this is a frozen tuna bin, and you could use an optical character recognition algorithm to basically track maybe bins coming in and out of a cold storage. So you have a better idea of the movements of these bins throughout a large scale inventory. So those are many of the different types of use cases. As I said, I think primarily it is quality control, but you could also use it for production. And the other thing that I think is interesting is many of the new computer vision cameras that are out on the market could actually run multiple models. So you could use a camera both for tracking productivity, but also quality control at the same time. And finally, I'll just kind of wrap up our presentation portion by talking a little bit about the future and what some of the opportunities and challenges are. I mean, I actually think that the use of AI for visual inspection could be a paradigm shift in how we do quality control in the industry. And I say paradigm shift because what we'll be doing is moving from random sampling, where in some cases, like only a fraction of a percentage of raw material or finished goods are actually inspected, to continuous 100% inspection. So in a very large scale tuna cannery where you're producing 1 million cans a day, we can take a picture of 1 million cans and store it in the cloud. So there's huge opportunity to have 100% inspection throughout the supply chain. We'll also be moving from human inspection, which could be quite inconsistent, particularly if fatigue sets in with workers, to very consistent. Also, we know that humans can be quite biased. If you ask two people what the quality of a particular fish is, they may come up with two different rankings. Whereas with the AI, it can be unbiased, or what I would call controlled biased. So where you can actually control and maybe measure the bias and understand it very clearly. Obviously, humans can be pretty slow in inspection, where automated cameras are very fast. And then finally, where you could move from maybe manual grading and sorting to fully automated, where using the camera could be sending a signal to an automated sorter, which then would automate the sorting process as well. So this will likely have implications for what the role of humans versus machines are in automated inspections. We're not, I know there's a lot of talk about getting rid of humans because of AI. I don't think that that's going to be the case in seafood inspection, particularly because the risks are so high around food safety. But the roles of machines versus humans could change. And I think we might move towards more of an oversight role for humans, where humans would be defining the standards, reviewing the outputs of the AI, handling what we call edge cases, or really difficult cases. We'd still have a role of refining the models, as Melina pointed out, monitoring the bias to make sure that the AI isn't biased, and then overall continuous improvement. So constantly retraining and improving the AI. Whereas the AI itself will likely be more doing this sort of the frontline inspections. So it's really great at repetitive tasks that are high speed, that could be autonomous. We can also start to look at what's called multimodal AI, and that is we might combine production, computer vision, and either other sensory data for the inspection. So instead of just an image, you might be able to pull different data from different sensors to do an inspection. So making it much more complex. And then, of course, once we have huge volumes of data, we could actually have predictive analytics, so that you could even predict what the quality of a product might be based on a whole bunch of parameters over a 2 or 3 year period where you've collected a lot of data. You could start to see patterns and predict what the quality outcomes would be. And so all of this is going to lead to, in my view, what I call the data deluge. So basically, the volume of data that's going to be collected for quality inspection is going to be huge. And this is where potentially generative AI, these large language models that we all hear about and are playing with, like ChatGPT, could be used to analyze really large volumes of data. And potentially, generative AI could also maybe find hidden insights or even patterns in this data that we don't recognize today. So I do think that there is a lot of potential for sort of layering on AI, where you might have computer vision as a sensor, cameras collecting data, but you might have some generative AI actually helping out with the analysis. So that's almost a wrap on our presentation. I just want to also have a bit of a shout out to some of our partners who've helped to fund a lot of our computer vision research over the last number of years, including Canada's Ocean Supercluster and the Canadian Food Innovation Network. The other thing I'll say is that we can't do any of this without our partners. So in the canned seafood, Bolton Foods and Eurofish in Ecuador have been huge partners in helping us with a lot of our AI. And Orca Specialty Foods and Circle Seafoods in British Columbia and Alaska have also worked a lot with us on salmon problems. And it's really important, I mean, to partner with industry players because we need data to train the AI. So it's really important for any kind of technology company to have really good partners that are basically industry players. And finally, I'll just put up this QR code if you scan it, and you'll get a copy of this presentation. We have on our blog, on our website, an article that goes through a lot of the concepts and ideas that were shared in today's webinar. So it's a bit of a takeaway from the presentation. And finally, here's just my contact details. So if you have any questions that you want to chat with us one-on-one about, particularly if you have any challenges in your supply chain or production process that you think could be solved by computer vision, we would love to chat with you. The one thing that has really excited me is that anytime I've presented a lot of this technology to processing plants and others, many of the production managers and QC managers almost immediately come up with new ways to use the camera in their facility. So I think that it's a very versatile technology with a lot of different uses. And I think we've only really seen the tip of the iceberg. I think there's still a lot of things that the technology can do. And I think it's going to come from people who day in and day out work on the plant floor and in the supply chain. I think that you're the ones who know what the challenges are. We know a little bit about what the technology is. So when those two come together, that's when we can really kind of help to solve some of the industry's pain points. And I'll leave it there and maybe open it up for any questions.
Thank you, Eric. So we're now moving into our Q&A portion of today's presentation. If you haven't already asked your question, or if you think of another question, go ahead and type them into the Q&A box, and we will do our best to get through as many questions as we can. We do have a question here. Our first question, I believe you already kind of covered this, but if you want to just circle back and maybe put it in a little bit more detail here. We had someone ask, how does the AI-enabled smart camera system differentiate between high quality and low quality seafood during inspection, especially in real-time operations?
Yeah, I mean, I can just quickly cover that. I mean, so it's basically visual. So anything that is visual is how the camera can determine. So I know in Nalina's example, she talked about maybe there being a piece of metal in a tuna can. That metal would need to be visual, of course, in order for the camera to pick it up. It's the computer vision. It's not X-ray. It can't kind of see inside things. So everything has to be visual. So it could be texture, it could be color, and it could be some sort of unusual defect, as we mentioned.
Another question here. Is the AI model trained to do grading in the shrimp industry? And if you know, is it already, or has it already been implemented with any companies in India?
I'm not aware of it being deployed in India yet. I think it's still new in the shrimp industry. I know Latrim, they have been using some laser technology for grading the size of shrimp with some of their smart machines. But to my understanding, it has not been deployed in India for shrimp inspection. And us as a company, we're just starting to do data collection and start to look at how we could build out models for the shrimp industry.
Another question here. Christy says, thank you for this interesting presentation. Have you done any work on or at at-sea factory trawlers? And how do you envision translating this technology to fishery monitoring in real time?
Mm-hmm. Yeah, so there are a number of companies who are doing, electronic monitoring of the commercial catch. And there's even some companies who are now putting video cameras, inside trawl nets and this sort of thing. For us as a company, we're very much focused on the inspection and the processing part. So if there is a factory trawler, there's a number of things that we could do in terms of the inspection on the processing, whether it's labeling inspection or size inspection, and this sort of thing to automate it inside the processing. The one thing about the type of computer vision that we're doing, we're generally working in very controlled environments. A lot of processing plants don't even have windows. So the lighting inside the factory does not change throughout the day. It's a very standardized lighting. Whereas, electronic monitoring out on the deck of a boat, for instance, so if you're counting fish coming over the side of a boat, it's a much more difficult computer vision problem because of the weather, the time of day, the back of a boat. One back of a boat looks different from the other back of a boat. For us, even though the conveyor belts in one factory might be a little bit different, they're not that much different. They're generally in blue or white or sometimes maybe even green, but it's a very controlled visual environment, which actually makes it a lot easier compared to putting a camera out on the back of a trawler and trying to track, fish coming over the deck of a boat. That's a very difficult computer vision problem. The industry is still working on that one.
Another question here. How do you see the future of seafood inspection evolving with AI over the next 5 to 10 years?
Maybe, Nilina, maybe I'll hand that over to you if you want to maybe talk a little bit about maybe where you see things going, maybe from more of a the technical side.
Yeah, so in terms of algorithms, I think we have new coming, which is increased accuracy, increased precision, and all of that. And from a user perspective, I think, like Eric mentioned, we're going to be also interfacing with large language models. Let's say so we have this computer vision model up and running, and we have all these results and predictions out, and the quality manager just asks okay, how did the cans look today? How many of them were defective, or how many fillets were defective? So people can just ask questions, and there's a generative AI, a large language model that actually runs over these predictions, brings up statistics, and gives you all the results. So that could be one kind of, where we can move into. Another would be from a technical point, like from a data scientist point of view, instead of even from the perspective of collecting images. Maybe I just have a few reference images of certain defects which occur very rarely. I can use LLMs to generate more samples of such images. I can describe the defect and say, okay, I need such images in my data set for the model to learn. So I need some images of this kind of fish to be generated with this kind of defect. So I think there's interesting ways in which the work that we are doing currently would be much more efficient and much more faster given the technology growth. So yeah.
And just on the hardware front, I'm always surprised at just the advances in the hardware. So we're not developing any of the actual cameras themselves. There are a lot of companies producing computer vision cameras, and recently the company that we used, they put out a new camera which is maybe about 30% more expensive as a new version, but it had 10 times the computing power than the previous version. So there's this idea of Moore's law that the cost of technology keeps going down while the power is going up exponentially. And I think we've seen that, even recently with some of the advances in the computer vision hardware.
Awesome. Thank you for that. So that does seem to be our final question for this session. Before we close out today, I do have some just very quick housekeeping notes to cover. If you could please fill out the short evaluation form that will appear on the webinar console shortly. This will help us better serve your needs in future webinars. As a reminder, the on-demand materials will be emailed to everyone within 2 business days. This will include a PDF of the slides as well as a link to the recording of today's presentation. And again, everyone will automatically receive that email within 2 business days. Thank you again to Melina and Eric for a great presentation today, and thank you to all of our attendees for taking the time out of your busy days to join us. This webinar was brought to you by Seafood Source and sponsored by ThisFish. Thank you all and have a great day.
Thank you.
Thank you.